All right. In this module, we will talk about two very important concepts: total probability theorem and Bayes theorem. So to motivate total probability theorem, let's think about in a more abstract way first, and then we'll work out an example to make it very crystal clear. So imagine I have a sample space S. So I'm going to just sort of represent it in an abstract way. Okay. So think of things inside this box represent my sample space, set of all outcomes. Okay. Now, imagine I have some event A that I want to study, and I'm interested in finding the probability of this event A. Okay. Now, the event A might be a very complicated object to analyze and study. Okay. Now, one would love to do the analysis of A, understand the probability of this complicated event happening by somehow breaking this calculation down into smaller pieces. Okay. And this breaking down process is what, in a sense, is provided to us by the total probability theorem. Okay. So the starting point is the following, that we take our original sample space and we break it down into a partition. So we partition the sample space. Okay, so what do I mean by a partition? Visually, this is what it means. So let's say I take my original sample space and I sort of think of breaking it down into chunks. Let's say these are some chunks that I broke it down into. Okay. So call this as chunk A1, A2, A3, A4, A5, and A6. Okay. Imagine understanding these chunks is relatively easy. Okay, so suppose that the partition of the sample space happened in such a way that understanding these guys and anything inside these partitions is easy. Then we can always think about A as being broken down as follows. So think of A will have some intersection with some of these partitions. So it will have intersection with A2, which will be this pink part. It may have, in this figure, it has intersection with A3, that is this part. And then it will have intersection, in this example, is this with A4, that is this purple part. Okay. So you can think of, informally, the probability of the event A is the probability of the pink part, the probability of the teal part, plus the probability of the purple part. So if I were to just sort of draw visual boxes here to give you a feel of what is really happening, this is what you would be able to do, right? At least just looking at this thing visually. Right? So hopefully everybody will agree that this sort of makes sense, at least conceptually, by this Venn diagram. Okay. Now, what total probability theorem does is that it formalizes this thing in a very precise way. Okay, so now I'm going to write it down. So here's the statement of total probability theorem. So let me write it in a box. So this will be the statement of total probability theorem. So it says the following, that let A1, A2, dot A sub n be a partition of S, which is the sample space. Then for any event A, we can write the probability of A as follows. We can write it as the probability of A1 times the probability of A given A1 plus probability of A2 times the probability of A given A2 plus all the way till AN times the probability of A given AN. Okay. What are these guys, in fact? So if you think about each term, what is this guy? If you remember from our module on conditional probability, what was conditional probability? P of A given A1 was probability of A intersection A1 divided by P of A1. So this is nothing but the probability of A intersection A1 plus the probability of A intersection A2 all the way till P of A intersection AN. So I hope it is clear to you now, connecting this formal definition to this visual Venn diagram interpretation. So if you think about A, the event A, it has no intersection with A1 in this figure. So the probability of A intersection A1 is 0. So that's why it does not appear on the right-hand side. However, A intersects with the pink part, A2, intersects with the teal color, A3, and with the purple one, A4. And that's what you see. These are the sum of the three non-zero terms that you see on the right. Okay. Now, how do we prove this result? Proving this result is very easy. So let's, while we are at it, we can actually prove it in a couple of lines. So we start with the event A. Event A can always be written as intersection with the sample space. Okay. Now, what is the partition? Remember, this is where we're going to bring the partition. S can be written as a union of A1 union A2 all the way till union A sub n, right? Because, why is this step true? This is since A1 till AN is a partition of S. That's the definition of a partition. That partition of S is a bunch of sets which are mutually disjoint. And if I look at the union of A1 till AN, they'd give me back S. Okay, that's the definition of a partition. Once we have that, then we can use our properties of intersection and unions. We can write this as A intersection A1 union A intersection A2 union ... all the way till A intersection A sub n, right? Now, when we take the probability, so probability of A will be the probability of this bunch of things, A intersection A1 union A intersection A sub n. Now, let's think about these guys. What are these guys? These are some events. They are mutually exclusive. All of these are mutually exclusive. Why are they mutually exclusive? Because A1, A2, AN are mutually exclusive. Therefore, A intersection A1 has nothing in common with A intersection A2. Okay. Now we can apply our probability axiom that probability of the union of mutually exclusive events is the sum of those probabilities. So we apply our axiom number 3 of probability, and this will end up being a sum A intersection A1 plus A intersection A2 and so on and so forth. And there we have it. And then we can apply our, A intersection A1 can be written as P of A1 times P of A given A1 plus P of A2 times P of A given A2 and so on and so forth. This completes the proof. Let me just make sure I... Okay. So this completes the proof of total probability theorem. Let's try to work out one more simple example to see this in action. Now, suppose we have a class of students. Suppose a class has 60% girls and 40% boys. Okay. We are also given that suppose 30% of girls have long hair. Again, this is just a textbook example. And suppose that 20% boys have long hair. Okay. Now, here is the experiment. So this is the setup. And then what we do, we pick a student at random. we pick a student at random, and then we ask, what is the probability that the chosen student will have long hair? Okay, so this is the event of interest that you want to analyze. So this is your event A, that whose probability you want to find. Student having long hair, right? And this is the setup this is provided to you, right? In many things, in many times where you encounter probability problems in real life, you will not be given a sample space. You will have to conceive and think about and formalizing the sample space. So it's always good to work out problems which are stated in natural language, but then you have to think yourself as to, what is the sample space? What concept am I supposed to use here? Okay. So let's try to break it down. So let's think about, let's call event A as student with long hair. This is the event that we want to understand. So we are interested in P of A. Okay. Now, what is our sample space? Our sample space has students, out of which 60% are girls and 40% are boys. Now, clearly, this is a partition of the sample space. So we should define A1. Suppose we define A1 as the set of girls, and A2 is the set of boys in the class. Okay. Hopefully, it is clear to you that A1 intersection A2 is the empty set, and A1 union A2 is my sample space, which is the set of all students, which means A1 and A2 is a partition of the sample space. Once we are in this business, then we can apply total probability theorem. Total probability theorem says that for any event A, we can break it down as the probability of A intersection A1 plus the probability of A intersection A2. Okay. Now we also know we can write this guy as probability of A1 times the probability of A given A1, plus you can also break this down in a similar manner, P of A2 times the probability of A given A2. Okay. Let's think about each one of these terms. The probability of A1, what is this thing in words? And this thing is just the probability of picking a girl from the class. How many girls are there? 60% girls and 40% boys. So what's the probability of picking a girl? It's 0.6, 60 by 100. Okay. We'll worry about this term in a bit. Let's take care of PA2. What is PA2? Probability of picking a boy. This is 40 by 100. Now we have to worry about these two terms. Okay. What is this conditional probability? So A given A1 means, refers to the event that girls, given that you have picked a girl, so A1 is the event of picking a girl, and A is the event of long hair. Among girls, what do we know? 30% of the girls have long hair. So among girls, if a girl was picked, there's a 30% chance that she will have long hair. And similarly, if a boy is picked, then there's a 20% chance that the boy will have long hair. So what are we really provided is this probability of A given A1 is 30 by 100, and A given A2 is 20%, so 20 by 100. You put all these things together, you get 18 by 100 plus 8 by 100. So you get 26 by 100. So this is the probability of the event A. So hopefully this example shows you the power of total probability theorem. At the end of the day, the game here is to think of a complicated event and breaking it down into simpler events which you can analyze. Okay. Okay. All right. Now, with this taken out of the way, let's now talk about the next important concept that I want to cover in this module, which is which is Bayes' theorem. So Bayes' theorem, as such, is pretty straightforward. It says that let A and B be two events of positive probability, so they must not be zero probability events. Then, if I want to write down probability of A given B, do we know about conditional probability? I think we have done this many times now. Hopefully you are comfortable. So we can write this as probability of A intersection B by the probability of B. We have seen that. Now, interestingly, we can also write down the probability of B given A. What is the probability of B given A? It's the probability of B intersection A divided by the probability of A, correct? So from here, we can write probability of B intersection A as a product of P of B given A times P of A, right? And what Bayes' theorem does is essentially utilizes this simple fact and allows us to write down this numerator term as P of A times the probability of B given A divided by probability of B. Okay. So in some sense, there is not much if you just look at the formulation in terms of just the mathematical formula says it's. But I think there's a lot of value in thinking about what do these terms actually mean. Okay, so let me try to give you some interpretation behind the operational meaning of some of these conditional probabilities. So in statistics, so I hope this is clear. So if I were to just recap and rewrite this thing, it just Bayes' theorem is saying P of A given B can be written as P of A times the conditional probability of B given A divided by the probability of B. Okay, so if you were to just remember one single formula for Bayes' theorem, this is perfectly fine. Okay. Now, what are the interpretation of these terms? So I want to talk about all of these four terms and try to give them an interpretation. Okay. So let's think about them. Suppose you're interested in some event A. Suppose you were interested in some event A, in analyzing A. And you were able to find the probability of A. Okay. So oftentimes in literature and statistics, you will see to this object as referred to as the a priori probability. Okay. So to put it in context, let's take an example. Suppose we think about predicting whether it's going to rain or not. Okay. So let's say I ask you, what is the probability? So that let's say I ask you, what is the probability it will rain in Tucson, Arizona? maybe you're going to look at the historical data and you're going to say, okay, the probability, without any other additional information about today, it will rain. So let me add today evening in Tucson, Arizona. So you'll give me an estimate. Okay, I took some data and my estimate is, maybe 0.1, 10% chance of rain. Okay. So this is like the a priori probability without any additional knowledge, just purely based on historical data. Now, let's say you do some measurement, okay, and you observe some data. You observe, collect some data, and you make some deductions out of it. And let's call those deductions as B. So for example, you find humidity is 90%. Okay. Now, given this additional information, you would love to revise your estimate. What's the probability of A given B? Or in other words, what's the probability of will it rain or the chance of rain given humidity is 90%? So what do you think? The answer will not necessarily be the same as 10%. Your estimate will potentially change, right? Now this object, A given B, is also referred to as the A posteriori probability upon observing B, or given that event B has occurred. Okay, so these are two important concepts. Keep in mind. If I just look at P of A, in many scenarios, people love to call it A. What is A priori probability of something happening? And A given B is often referred to as the A posteriori probability of A happening, given that you have seen something or some event B has occurred. Okay. So now if you think about Bayes' rule, what is Bayes' rule actually doing? Bayes' rule is saying that P of A given B is P of A by P of B times P of B given A. Okay. So in some sense, if you think about this as your A posteriori probability, then it's relating you to the A priori probability of A, the A priori probability of B, and this is referred to as the conditional probability of B given A. Okay. We don't usually refer to B given A as a posteriori of B given A, but typically it's just by conventional naming, it's called the conditional probability of B given A. Okay. So these are the A priori probabilities of A and B respectively, and this is just the conditional probability. Okay. All right. Now let's introduce a very important concept, something called independent events, okay, which is very much related to a posteriori and prior probability. So we say two events are independent so we say that events A and B are independent if any one of these things hold. A condition on B is same as the probability of A, and which is the same as saying the probability of A intersection B is the probability of A times the probability of B. Okay. Why does this thing make sense? Let's think about this. What's the left-hand side? Left-hand side is the probability that what's the likelihood of A happening given I told you that B occurred. What is the right-hand side? Right-hand side is without any knowledge, I would have to predict what's the likelihood of A happening. If the happening of B does not change my estimate about the likelihood of A, then I say that B does not influence A in any way, and therefore they are independent of each other. Okay, so hopefully that makes it clear. To give you an example, suppose in our previous setting, A was rain in Tucson, and B is Tesla stock went up to $5,000. So if I told you the probability of A is 0.1, 10% chance, and let's say the probability of B is 0.6, 60% chance, and I told you that B also occurred, that today, in 2025 sometime, for instance, the stock went up to 5,000. Do you think my estimate of rain in Tucson will change given that Tesla stock went up to 5,000? You would clearly say, no, not at all. So this will be the same as the probability of A, which means this event has no bearing on this event whatsoever. No relationship in some sense. Okay. So that if that's the case, then we say that events are independent of each other. Okay. We can generalize the concept of independence from two events to any arbitrary number of n events. So let's spell that out. So we say that n events A1, A2, all the way till A sub n are independent if any k less than n of them are independent. So more generally, basically, if I look at any subset, say AI1 intersection AI2 intersection AIK, for any k, this should be the product of the probabilities. AI1 times AI2 AIK for all k to give you an example. Suppose I have three events. What would make these three events independent? What kind of conditions will I need? I will, of course, require a pairwise condition. So A1 intersection A2 must be PA1 times PA2. Similarly, A1 intersection A3 will be PA1 times PA3. And PA2 intersection A3 must be PA2 times PA3. And you would also like this condition to be satisfied, that the probability of intersection of all three must be equal to the product of the individual probabilities of the events. If that's the case, then we say, yes, the three events are independent. It may happen that only three are satisfied, but this one is not satisfied. Then those events will not be independent. Okay. All right. So I'm going to close this module by giving you a few examples, maybe one or two examples, working out the concepts of Bayes' theorem and independence along the way. Okay. So let's work out a couple of examples. So imagine I have I have two boxes. So I'm going to sort of not necessarily sort of write everything down in words, so but imagine the following. So I have, let's say, two boxes. This is my box 1, and I have another box 2. Okay, and each box has a certain set of balls. Okay, so this box has alpha number of white balls in it. alpha of them, and then it also has beta black balls in it. Right? Similarly, box 2 has delta, alpha, beta, delta, gamma are some arbitrary integers. Okay. You can pick your favorite numbers and plug them here for fun. Okay. What's the experiment? So we pick a ball at random without looking. We put our hand inside the left box, box number 1. We don't know which one we're going to pick, either white or black, but at random. And transfer, so ball at random from box 1, and transfer to box 2. Very simple experiment. So this is our first step. We pick a ball from random from box 1, put it in box 2. Okay, so we take a ball from here and put it here. One ball at random. Then what's the next thing we do? We draw a ball. We then draw a ball at random from box 2. Okay, and we ask, now here's the event we're interested in. What is the probability it will be a white ball? Okay. So let's see what can happen. You're gonna apply all the things that you've learned so far and try to work it out. Okay. So when we pick a ball from box 1, what are the two possibilities? We'll either pick a white one or we'll pick a black one, right? If we pick a white one, then the number of balls in box 2 will become delta plus 1 white and gamma black. Gamma will not change. On the other hand, if we pick a black one, then gamma will become, the new number will become gamma plus 1, while white will remain the same, right? Okay. So let's write down this in terms of two possible outcomes. So we can think about it like this. So two outcomes are possible in the first step. In step 1. Let's denote W as the sort of white event that a white ball is transferred to box 2. And B is the event that a black one is transferred to box 2 from box 1. Now, what do you think are these two kind of events? If you think about step 1, what is the sample space of this thing? It's basically these two events. Either W happens or B happens. One of these two things will happen, right? Okay. So what is the probability of W? Probability of W is nothing but the probability of picking a white ball from box 1. How many white balls does it have? It has alpha white balls out of how many total balls? Alpha plus beta. So that's the probability of W. What is the probability of B? It's the number of black balls, beta, divided by the total number of balls, alpha plus beta. Clearly, a sanity check is in order. PW plus PB better be 1, because that is the sample space. Okay. Now, a quick quiz for you. So first thing is, are W and B mutually exclusive events? Yes, absolutely. If W happens, then B doesn't happen. And if B happens, then W doesn't happen. So the answer is yes. Okay. Now, are W and B independent events? And I would love you to pause the video and think yourself whether are W and B independent events or not. The answer is no. Why is that? Let's look at the definition of independence. So if we want to show the probability of W given B, it is what? It's the probability of W intersection B divided by the probability of B. That's the definition of W given B. What is probability of W intersection B? W intersection B is when W happens and B happens. Oh, but we know both of them cannot happen simultaneously. Either you pick a white ball or you pick a black ball. So this is 0. Okay, is this equal to the probability of W? No. So clearly they are not independent events, right? Okay, so they are not independent events. Okay, now let's come back to our example. So remember, we were interested in computing the probability in the second step. When we pick a ball from box 2, what's the probability it'll be white? Okay, so let's again give it a name. Let's call it an event A. So event A is drawing a white ball is drawn from box 2 in the second step, in the second step. Okay. Now we're in a game of applying total probability theorem. So we know W and B are a partition of the first step's sample space. So we can write P of A as P of a white ball being drawn in step 1 times this event A happening given W plus the probability of a black ball being drawn in step 1 times the probability of event A happening given B. Okay. Let's think about each one of these guys. This guy we computed, P of W and P of B. This is great. So we have these numbers in place for us. What is P of W? Let's see, alpha by alpha plus beta. And this is beta by alpha plus beta. So these are good for now. Let's worry about these other terms. Now, what is A given W? A given W is the event of drawing a white ball from box 2, given that a white ball is drawn from box 1 in step 1. So let's see what is the situation when W occurs. Now, to think about A given W, let's look at box 2. So given W, box 2 will look like what? Originally, box 2 had how many balls? Delta white balls and gamma black balls. If a white ball is drawn from box 1, then what's going to happen here? I'm going to have delta plus 1 white and gamma black. Given W, this is the status of box 2. So what is the probability of drawing a white ball from here? It's number of white balls now, delta plus 1 divided by the total number of balls, which is delta plus 1 plus gamma. That's this conditional probability. And then you can run the same thing for A given B. So if you were to write this down, so this will be delta white and gamma plus 1 black given B, and my situation will look like delta white balls divided by total number is delta plus gamma plus 1. So that's my final answer at the end of the day. Okay, so with this hopefully clear, we're going to stop this module and resume next. Thank you.